In the previous two lectures, we have seen two recurrence formula for ln of x. In fact, I have mentioned here all those two formula which we have studied in the first two lectures before this. The first recurrence formula you have studied, this is ln plus 1 of x plus x minus 2n minus 1 ln of x plus n square ln minus 1 of x equal to 0. And the second recurrence formula which we have studied was ln prime of x equal to n times ln minus 1 prime of x minus ln minus 1 of x. You have seen in the previous lectures that these two recurrence formulas were proved by using the generating function expression for ln of x. And so these two formula have independent proofs. Now we are going to discuss the third recurrence formula for ln of x. And this third recurrence formula I have mentioned here already. This is x ln double prime of x plus 1 minus x ln prime of x plus n ln of x equal to 0. In fact, you will see that this third recurrence formula can be proved by using the first and second recurrence formula. So there is no need to start with the generating function expression or any independent proof. You should start with the first recurrence formula and the second recurrence formula, and then after some mathematical operation you will get this third recurrence formula. So for this we must remember these two recurrence formula which we have already studied. So let us start with the first recurrence formula which I have mentioned in this equation A. In fact, as you can see in this third recurrence formula, there is a second order and first order derivative of ln of x. And in this first recurrence formula, there is ln of x, not its derivative. So definitely if you if you want to prove this third recurrence formula by the help of a recurrence formula defined in A, definitely you should differentiate this result defined in A with respect to x 2 times. So first of all, we will differentiate this equation A with respect to x. So differentiate equation A with respect to x. If you will differentiate equation A with respect to x, what will be the result? You can see this first term. This is just a function of x, so this will be simply ln plus 1 prime of x. So first term will be ln plus 1 prime of x and plus the second term. As you can see in the second term there is a product of two functions. First one is x minus 2n minus 1 and another is ln of x. So we will apply here the rule for the differentiation of product of two functions. So first of all we will take this x minus 2n minus 1 at each and differentiate ln of x. So the second term will be x minus 2n minus 1 and dc of ln of x, that will be ln prime of x. Now we will keep this ln of x at each and differentiate x minus 2n minus 1. You can see the dc of x minus 2n minus 1 will be what? This will be simply 1, because dc of 2n and 1 will be 0 and that of x will be 1. So this is simply ln of x. ln of x. This is ln of x. Now see the next term. The next term is n square ln minus 1 of x. N square is a constant factor, so its DC will be ln minus 1 prime of x. So this is n square ln minus 1 prime of x. Now we have obtained the first order derivative here, but we also need the second order derivative. For that we will again differentiate this equation with respect to x. So again differentiating with respect to x, we get what you will get. You can see the DC of this term will be ln plus 1 double prime of x. This is second order derivative. And plus, again you can see here is a product of two functions. So the first term will be x minus 2n minus 1 ln double prime of x. And then we will differentiate x minus 2n minus 1, which will be in fact 1, and the remaining term will be ln prime of x. Now we will differentiate ln of x. So this ln of x will be what? This will be ln prime of x and plus, in fact this equal to 0, this equal to 0, and plus now DC of this much, this will be n square ln minus 1 double prime of x, and that will be equal to 0. This is equal to 0. Now we will replace n by n plus 1 in this equation. So after replacing n by n plus 1, what you will get, you can see, replacing n by n plus 1. This equation yields what you will get. You can see n will be replaced by n plus 1. So in first term you can see this will be ln plus 2 double prime of x and plus x minus 2n, but n will be replaced by n plus 1. So this will be minus 2n, minus 2 and minus 1, that will become minus 3, and ln plus 1 double prime of x and plus, you can see, ln prime of x plus ln prime of x, this will be 2 ln prime of x, and n will be replaced by n plus 1. So this will be 2 ln plus 1 prime of x, and plus here n will be replaced again by n plus 1. So this will be n plus 1 whole square, and ln minus 1 will become ln double prime. This will be ln double prime of x, and this equal to 0. Say this is equation number 1. Let us see. Now we will see the second recurrence formula, which I have mentioned here in equation B, and for your convenience I am just repeating this second recurrence formula here So you can see what is the second recurrence formula. So according to second recurrence formula for ln of x, you can see what is this second recurrence formula. See again here, and as I have told you, you must remember it. So this, you see this, and I am just repeating it here. This is in fact ln prime of x equal to n times ln minus 1 prime of x and minus ln minus 1 of x. This is actually the second recurrence formula which we have already studied in the previous lecture. Now we will replace in n by n plus 1 in this equation. So replacing n by n plus 1. When you will replace n by n plus 1, what will be the result? You can see easily in LHS there will be ln plus 1 prime of x, and that is equal to n plus 1, because n is replaced by n plus 1, times n minus 1 will be now n, so this will be ln prime of x and minus ln of x. This result has been obtained simply replacing n by n plus 1 in this second recurrence formula. Now we will differentiate this equation with respect to x. So differentiating this with respect to x, we get, when you will differentiate it, you can see very easily what will be the result. This will be simply ln plus 1 double prime of x, and this is equal to, since n plus 1 is a constant factor, so it will be outside of the operator, and when ln prime of x will be differentiated with respect to x, it will be simply ln double prime of x and minus ln will be now differentiated, and this will be l prime n of x. So this is the result which we get after differentiation with respect to x. Now say this is equation number 2. This is equation 2, let us say. Now we will differentiate I have differentiated it and obtained this result. Say this equation is in fact 2 and this equation is 3, because we will need also this equation 2 here. Now again we will replace n by n plus 1 in this equation. So you can say on replacing n by n plus 1, we get, what will be the result? You can see, since n is now replaced by n plus 1, so you can see in LHS there will be l n plus 2 double prime of x, and here n is now n plus 1, so this will be n plus 2 times l double prime n plus 1 of x and minus l prime n plus 1 of x. Now we will use this value of ln plus 2 double prime in this equation 1. You can see here. You can see the equation 1 here. And in this equation 1, the first term is ln plus 2 double prime. And we have already obtained the value of ln plus 2 double prime here. You can see. So use this value of ln plus 2 double prime of x in that equation 1. So you can say substituting this value of ln double prime, this is ln plus 2 of x in 1. When we will use this value of ln plus 2 double prime in equation 1, what will be the result? You can see. This will be, in fact, see first of all equation number 1. This is your equation 1, and here is ln plus 2 double prime of x. So we will replace this first term here, and this will be n plus 2 times l n plus 1 double prime of x minus l n plus 1 of x prime, and the remaining term is written here directly. This is x minus 2n minus 3 ln double prime of n plus 1. Here is actually, you can see, l double prime n plus 1 of x and plus, see the first equation again. I have written this term. Now there is 2ln plus 1 of x prime, 2ln plus 1 prime of x. So write it. This will be plus 2 ln plus 1 of x prime, and plus, what is the next term? You can see here. This is n plus 1 whole square ln double prime of x. So this will be n plus 1 whole square ln of x double prime, and this is equal to 0. Now let us simplify it a little bit. You can see this is, when you will multiply by this n plus 2 to the inside terms, this will be n ln plus 1 of x double prime and minus n ln plus 1 prime of x plus 2 ln plus 1 double prime of x and minus 2 ln plus 1 of x prime and plus, now see this term. This will be, in fact, x ln plus 1 double prime of x minus 2n ln plus 1 double prime of x and minus 3 ln plus 1 of x double prime. And now see this term, this is plus 2 ln plus 1 prime of x and plus n plus 1 whole square, n plus 1 whole square ln of x double prime, and this equal to 0. Now see here, this you can see this term will be simplified in this manner. You can see here, this is, see, first of all, ln double prime of x is present here, and also it is present here 2 ln plus 1 double prime of x, and there is minus 2 ln plus 1 prime of x, and this much, and here is plus. So this and this will cancel out, and we will associate this 2n ln plus 1 double prime of x, and here is n ln plus 1 double prime of x. So this will be composed, this term and this term will be composed, and we will get n ln plus 1 double prime of x. And again this ln plus 1 double prime is also present here, and after that it is present double n double prime is present here also, but this is minus 3, and one term is present here. You can see this result will be now taking this ln double prime ln double prime n plus 1 of x. This will be taken common, and this will be x minus n minus 1 ln double prime of x minus n ln prime ln plus 1 prime of x plus n plus 1 whole square ln double prime of x equal to 0. So you can see here this nl prime n plus 1 of x, and is present already here, and after associating the terms we get this result. Now we will substitute for ln plus 1 prime from this equation. You can see here in this equation 2. In equation 2, ln plus 1 prime of x has been defined, and so we will substitute this value of ln plus 1 prime in this equation at the place of this ln plus 1 prime. So putting the value of ln plus 1 prime of x from equation 2 in the above equation, we get you can see when you will substitute this value and simplify, you will simply get x ln double prime of x plus 1 minus x ln prime of x plus n ln of x, and this equal to 0. And you can see this equation is nothing. This is simply the Laguerre differential equation, because you know the Laguerre differential equation has the solution Laguerre polynomial ln of x, and you know what is a Laguerre differential equation. This is x y double prime plus 1 minus x y prime plus n y equal to 0. And you know this equation is Laguerre equation. Laguerre equation, and this equation has solution ln of x. So this ln of x must satisfy this Laguerre equation, and this is actually the Laguerre equation, where you can see y has been recognized by ln of x. So this is simply the Laguerre differential equation. So we have in the 3 lectures we have seen the 3 recurrence formula for ln of x, and this is very important formula for solving the numerical problems.